Hello, everyone, and thank you for attending today's webinar, PFAS and Food Matrices Developments and Method Validation. In the short time I have today, I'm only going to talk about a few common interference related to PFAS analysis, and these are the organic compounds, the family of cholic acids or bile salts, such as TDCA and these other ones shown here. I'm going to talk about two approaches we're using in combination to mitigate these interferences specifically. And then briefly I'll talk about a new format to make the flow through and especially for high throughput labs a lot easier, and how we're going to apply this for food matrices. So specifically, TDCA is a known contaminant in environmental samples, and just as an example of that, I'm going to talk about this EPA 1633 for PFAS compounds. Many of you are probably very, very familiar with this method. I'm not going to talk about it too much, just talk about how it relates to this TDCA problem. But there's a lot of discussion about it in terms of the type of interferences that are co-extracted, and how it can be sections to remove and clean up and so on and so forth in this method. Validated for wastewater, surface water, groundwaters, and soils. It should be promulgated sometime in 2024. So specifically, the method talks about using TDCA, using removal or mitigation using dispersive graphitized carbon black. So a little bit of background here. This is a performance-based method, and what that means is that you can modify, make changes to the method and still be in compliance with the method if your goal is to overcome interferences, improve sensitivity, accuracy, or precision of the results, provided that you meet all the performance criteria for the method. So in this method, samples are extracted, whether water, soil, or so on and so forth, spiked, and you need to undergo some cleanup using carbon before your analysis. Specifically for the dispersive GCB, the method talks about adding 10 milligrams of carbon to each sample, as well as each batch of QC extracts using a 10 millimeter scoop. Then you shake the sample a little bit to mix the carbon in the sample. But they also mentioned something, and the bolding is something I added here to the presentation. They say it's important to minimize the time the sample extract is in contact with the carbon. And then they tell you to vortex it for 30 seconds to mix it well, and finally centrifuge it for about 10 minutes. So the purpose of this is to remove organic acids, humic, cholic acids, and TDCA is known to suppress ionization and interfere with PFAS analysis. Another approach I'll mention briefly is a stack cartridge, such as EnviroCarb or some sort of equivalent. It can also be used as part of this process. So there's some downsides to dispersive GCB that we hear a lot about. First of all, it's very time consuming. It can add about 45 to 60 minutes per batch of samples. In general, it can affect your precision, and simply the more manipulations you do are going to add to more variability, especially if PFAS sticks to surfaces, it gets pulled out differently, and going from maybe C4 to C18 carbon chain lengths, you're going to get different inherent properties for the PFAS. So you're going to lose some precision in general. It's also messy, just in a practical sense. This material is very hygroscopic. It's just very static. There's a lot of static to it. It can float up into your room if you're not using. Many people have to wear a mask when using this material. They talk about recovery issues. Remember that EPA warning where if you keep it in contact too long, so you have to keep moving, so there might be a little stress going on there. And finally, if you don't centrifuge it well, remove it out of your system, you're going to clog your column, your LC column. So it's going to get in the way. It's just kind of a messy stuff to work with. Now, the alternative to this is to use another cartridge. Where you have a separate tube following your solid phase extraction, but it's going to add additional time So a lot of things you're going to mitigate. It's going to be much more convenient to use another cartridge. But again, you're going to have to load the sample. You got to condition the cartridge, equilibrate, load your sample, wash it, and then finally elute. Just another SPE step, basically. And finally, it's going to add another cost. And for high throughput laboratories, that's a lot of money. Labs doing a couple thousand samples a month. One more thing about TDCA, it's also common in food samples. And I just have one paper here, Analyte and Matrix extension for per and polyfluoroalkyl substances in food and feed, published by Susan Ginaldi, where she talks about isomers of TDCA are known to interfere at this 49 to 80 MRM transition for PFAS, and very common in foods such as eggs, milk, liver, meat, and seafood. This method, of course, is food method, so it's using catchers, and then it talks about using GCB as well in the extract. And after the GCB, you're going to use an SPE car cleanup step to clean up the GCB and also concentrate the sample a little bit further. So again, we have a two-step process for the sample preparation for food matrices. So we just really asked ourselves a simple question after hearing a lot of feedback from our customers. How do we simplify this process a little bit? We got a lot of complaints. So we just basically said, well, why don't we just put the two phases in one column? And it is very, very common in our industry. And we thought, why don't we just put the weak anion exchange with the graphitized carbon black in a 6 mil tube format shown here. And here I have some additional photos of the material. The one on the left has the wax on top of the GCB. This is designed for water extracts. And the sample on the right is designed for soil and tissue extracts. And this is because the EPA method has these steps reversed within the method itself. So we made two different versions, whether you're doing a water sample or some sort of solid or biosolid sample. So the first thing we wanted to ask ourselves, okay, we have the stack cartridge. What do the recovery comparisons look like if we use the two different procedures? And this is from a surface water sample that was spiked with PFAS, 18 PFAS compounds. These are the isotopes. And if you look, we get different percent recoveries for the individual PFAS compounds. But the main point here is to notice that the bars are pretty much the same size. And the two different colors represent the different steps. So the blue represents the single stack cartridge, and the orange bar represents the weak anion exchange followed by this dispersive SPE cartridge. So we get equivalency at this one laboratory, courtesy of Alpha Analytical, for surface water samples. Now we did the same thing for a wastewater sample. Again, we're getting different heights, different variation recoveries for the different compounds. But again, the point we want to show is that there is very little difference between the two processes. So our goal of showing equivalency has been met. So we're meeting those EPA method requirements, but we want to simplify the analysis in the steps. So we're pretty much within the guidance of the performance-based method. Another example shown here, this was for spikes for 2 nanogram per liter, for PFAS compounds. And this was to do these low-level spikes were used for determining method detection limit. I know this is a little bit difficult to read, but we're just looking side by side between the two, looking at total percent recovery and total RSD of each spike. So for the strata PFAS, we get about 111% if we add those all up. And the two-step approach using wax plus DSPE is about 110%. So pretty much equivalent between the two for the total percent recovery. And finally, the percent RSDs are also very equivalent between the two. So moving on to soil samples, these are two examples shown here. This is a QC soil recovery comparison and also a proficiency test soil recovery comparison. So I should emphasize that, not all the PFAS compounds are going to be present. And they also vary in concentration, because the purpose of these samples is to determine what a laboratory can do if you're trying to get an ISO certification. So again, we see the equivalent results between the two approaches using a stack cartridge versus a dual step approach for a QC soil recovery and a proficiency test sample. So far we have equivalency whether using water, different types of waters, and different types of soil samples. So far, our results tell us that many laboratories have demonstrated equivalency and recovery and precision for the single stack cartridge. And it also reduces a lot of sample prep time. That's going to be about 30 minutes per batch of sample. It's going to lower material costs and also a lower labor cost. And it will ultimately increase productivity and throughput compared to the traditional two-step approach on sample preparation. So does the cartridge remove TDCA specifically? So in this example, we want to compare spike recoveries of TDCA versus PFAS in water samples. So looking at the far left of this table, we spiked TDCA at 125 micrograms or 500 microgram per liter final concentration. And we also looked at the ion transitions for PFAS, percent recoveries, as well as the C8, C13 labeled PFAS. For each sample, we used two different waters. So one is just a reagent water, and the other is using a TOC spike. And if we look at the white section of the table under the stack cartridge, we get some removal. So we spiked 125 microgram into these samples, and we get about 80 in the TOC back, and we get about 52 final in the reagent water. So some of it's removed. But if you look at the dispersive step, that didn't remove any TDCA at all. And if we compare this with the PFAS recoveries, we get excellent recoveries in this sample. So we're meeting method of compliance. So the good news is that PFAS is removed from the GCB, whereas TDCA is partially removed. So recoveries of PFAS between the two approaches, again, are equivalent, which is what we expect and what we've seen already. But the GCB and the stack cartridge, though it removes some, it doesn't adequately remove, a lot of the TDCA for these samples. So we need to come up with an additional step to prevent interference with PFAS. And this can be done with chromatographic resolution. Here we show an example just using our kinetics column showing how TDCA is about 2 minutes resolved from PFAS. So it's very, very easy to separate chromatographically. So switching on to food now for a typical PFAS extraction, spiking of standards, extraction, cleanup, and so on and so forth. Similar approach is used, except there's a catcher's extraction step, typically not typically done for environmental samples. And this has been well documented. This is an image from the Susan Ginaldi paper, and we're working side by side with her and the AOAC with the FDA for a partnership to explore a similar approach to address cholic acid interferences in a wide variety of food samples. So these are the next steps where we're taking the same approach that works for environmental to the food samples. So in conclusion then, cholic acids have been shown to interfere and exist in food and environmental samples. And by using this strategy, which is a combination of GCB and chromatographic resolution, can be used to mitigate their impact on quantitation of PFAS. Soon hopefully we'll have more data shortly showing our actual example in foods. These are ongoing as we speak, but we hope to get some of these in the stack cartridge specifically in validated method or applied to validated methods for food as well in our future. Thank you very, very much.